Everyone. So welcome to this class. So in this class today, I'll be talking about the content of my new book, which is Multi-Agent Orchestration Pattern for Enterprise Scale System. So the book is available on Amazon, it's available on Seller, it's available on Gumroad, it's also available on my website. So I'll be leaving all the link in the chat at the end of this recording, and please click and buy the book and leave a review, and also leave your email or my website for notification or newsletter. And if you have any consulting services on AI, agentic AI system, data engineering, data science, machine learning, please do well to contact us. We are experts and we deliver enterprise scale solutions, perfect and 100% reliable. Thank you. So in this lesson today, we'll be looking at the content of chapter 1 of the multi-agent orchestration pattern for enterprise scale system. And the chapter 1 talks about foundation of multi-agent orchestration in the enterprise, why enterprise should move from a monolith AI architecture to a specialized, coordinated, and orchestrated system that scale at large. So my name is Funke Yusuf. The English version of Yusuf is Joseph, and my other Yoruba name is also Dupe. So I am Funke Dupe. So you may be seeing a mixture of them. I am the same person. Okay. So the limitation of monolith AI in the enterprise. Of course, we know that monolith architecture is like a single architecture that combines everything, all the application together. It's not a microservice where application can exist independently, and the failure in one does not affect the failure in another. So in monolith AI system, you just have a single AI that will do everything. A single AI will act as a legal AI, it will act as a procurement AI, it will act as a supply chain AI, and the same AI will also be doing IT service, change management, site reliability engineering, kills testing, DevOps, and everything. So this is, a failure point. Single AI cannot be effective in orchestrating all the enterprise tasks, or the system will fail in no time. So large single model solution creates brittleness and maintenance burden that hinder organizations' growth. So organization that depends on monolith AI architecture using single AI to run every business activities, to solve every problem, cannot grow. Why? Because single AI cannot be effective in solving many problems across many departments. So they are brittle, that is, a failure in one internal component will compromise the system, the entire system, totally. Maintenance burden. So how will you maintain an LLM that is responsible for carrying out all the enterprise complex day-to-day activities? Any minor update require retraining the entire mega model, and you don't want to, waste time and effort and money on retraining model every year or every month because of a single failure. Transparency. This black box system lack the transparency required for auditability, so you will not be able to audit or trace the activity of the agent, and the agent will not give you optimal solution or across all tasks, because how can you program entire organization intelligence into one system? The system will be confused at some point, and it will not deliver uh, best practice to you. So that is why monolith architecture is become or has become totally outdated in enterprise system. All right, defining the enterprise multi-agent paradigm. How can we define enterprise multi-agent paradigm? Of course, we know that agentic AI system are systems that can act autonomously, plan, reason and act independently of human effort while still delivering optimal output. Okay, and they are trained on a base model, which are generative AI or LLM model, which acts as the brain of the agentic AI system. So it can be trained on LLM models like Claude, like OpenAI or Microsoft Copilot, and so on and so forth. Or you can even use a fine-tuned model as the base LLM, and then you build agentic AI system on top of them. So multi-agent paradigm, how can we define multi-agent from one single agent? Multi-agent paradigm is actually, many agents combined together to perform different tasks. You have many agentic systems built into one application, and each agent is responsible for a particular task. Multi-agent is different from tools orchestration. Tools are functions designed to solve a particular problem. Multi-agent are many agents designed to solve multiple problems, and each agent is a specialized agent. They have their own specialized skills for solving particular problem in the industry. So a shift from generalist model to a governed framework of interacting autonomous agents. So this multi-agent system also acts autonomously or with human in the loop to avoid mistake and error that is costly to the organization. So this is a shift from monolith agent, from designing single agent for the whole entire problem, to building specialized agents and orchestrating them together to solve problem while still acting independently. So this is the purpose of the book, how organization can orchestrate multiple agents in an enterprise or industry. So that is all the book look out for from beginning to the end. So the book talk about multi-agent orchestration, the design pattern, the governance, how to govern them, how to build the architecture, how the agentic system communicates, how to audit the agent, how to detect problem when there is a problem. So the orchestration layer of multi-agent system is what we look out throughout this book from beginning to the end, and we try to look at the design pattern using architecture diagram and codes. So this book does not teach how to build a production ready, like build full agentic system from beginning to the end. No, we teach design pattern, guide on how to design the architecture of enterprise multi-agent system for reliability, performance, governance, and auditability. So the MAS framework govern boundaries in legacy IT system. So it set boundaries. When you design a MAS framework, you are setting boundaries between agents. That is, agentic system, one specialized agent that is designed to solve IT problem cannot go and solve legal problem. The same agent cannot go and solve procurement or supply chain problem. No, you design one specialized agent for one particular business solution. Vendor analysis, specialized agent for vendor analysis. So just like you have specialized agent for IC system, you also have specialized multiple agent for vendor analysis or anything that relates to supply chain. Then you also have specialized agent for SOC and GDPR compliance. You have policy agent separated, and then you have negotiation agent for contract negotiation, which will not be the same as the agent that will do vendor analysis. Can you see the difference? So even though negotiation and vendor analysis are part of procurement management, we still have different agents doing vendor analysis and another agent doing negotiation. So you can see the separation of concern and how it works. So audit trail or centralized audit trails, and then all these agents we have a centralized audit trails where you can monitor and observe their activities and track their metric, their mean time, to recover, their mean time to failure, and the error or the error bugs, the reliability, and dependability and the performance. So they all have one observability framework. So this is how multi-agent framework are actually designed. Then orchestrated system, tracing the journey from siloed microservices to sophisticated coordination and explicit governance. So orchestration allow engineers to govern these specialized agents. These agents are not given the capability of talking to each other directly. No, there is a brain or there is a coordinator agent that acts as the general agent that links all these agents together and assign them a task, monitor their tasks, and see that they deliver correctly. So phase one, monolith AI, single large model uh, that will add to debug, scale, or update without full retraining. So in monolithic AI, we have just single agents designed to solve all the problems in all the departments, whether it is procurement, supply chain, IT management, legal, human resources, healthcare, and everything. One agent responsible for everything. That was the initial architecture. Then in phase two, that was in 2015 to 2020. Then in phase two, which is 2020 to 2022, agentic system moved to microservices. So companies begin to build microservice AI, which are specialized model for specific tasks, but lacking a coordination layer, leading to data silos. So the company started building many LLMs, generative AI, specialized for task, chatbots, and everything. But this agent lack coordination layer. They lack orchestration layer. They lack tools that will link them together and make them act as a single source of truth for enterprise solutions. And this leads to data silos. You have many LLM over there. You have many data, conflicting data, or duplication of data all over the company system. Then in 2022 to 2023, that was when early agentic system began. So reasoning capable agents with 2 use, or though coordination remain ad hoc and lack enterprise-grade fault tolerance. So around 2022 to 2023, early 2023 thereabouts. So there is, an upgrade in the microservice AI to early agentic system. But of course, there was no coordination, there was no orchestration, no predefined design pattern for the agent to communicate. And then now we are in phase four, which began from 2024 or let's say late 2024 to present, because the hype of this thing began in 2025. So we begin to have orchestrated mass, that is orchestrated multi-agent system, current state of the art, featuring explicit orchestration layer, standardized protocols, and architectural governance. So this is where we are today, building orchestrated, coordinated, specialized multi-agent system that work together to solve different problems while still delivering optimal enterprise solution with governance, auditability, and reliability. So reliable orchestration rules. So we don't just build orchestration. The orchestration must be based on, logic. It must be based on mathematics. It must be based on, autonomy, and it must also be based on strategy. So when these are combined together, mathematics, logic, strategy, and optimization, you have best practice, you have optimal output, you have a reliable system, and a reliable multi-agent system and multi-agent orchestrated layer. So rules ensure multi-agent systems are predictable and resilient. So rules make sure that you have a predictable, resilient, reliable, and performative multi-agent system. So we have a explicit coordination. So explicit coordinator, that is coordinator agent, coordinate via defined mechanism rather than emergent behavior. So we don't just leave the agent to coordinate themselves. No, you set a predefined rules, mechanism, logic for the agent to follow rather than emergent behavior. So because if you leave the agent to just apply any rules, though it may apply the rule that does not apply to a specific problem, resulting in, a loss or error, thereby affecting the company financial outputs and, efficiency. So single capability, agents should focus on capability to enable independent scaling. So orchestrated layer of agentic system or of multi-agent system should focus on capability to enable independent scaling. They should focus on what they are capable of doing, what they are designed to do, and they should enable independent scaling. That the scaling of the orchestration should not depend on the scale of other agents because they are loosely coupled. So that brings us to the next step, which is loose coupling. So agents depend on abstract interfaces rather than concrete implementation. So you can't, if you want to build agent, you can't just build a generic agent. No, because enterprise solutions are not generic. They require complex thinking, system thinking, and system design, and putting mathematical function, rules, and logic together to solve the problem. So you can't build a multi-agent system on concrete implementation and say you are building orchestrated layer. No, that orchestration layer is going to fail because it will not be able to handle the request of other agents. So orchestrated layers should be loosely coupled. They should be a standalone or agentic system and should depend on abstract reasoning and abstract interface, abstract functional programming, and design pattern. Then we have idempotency. That is, whenever you put, whenever you bombard the orchestration layer with different principles, different problems, it should give you, optimal, correct outputs at every time. So ensure same results when executed multiple times for safe retries. So whenever the orchestrated layer is executed, you should expect same results, not different result all the time. So that system will not be idempotent. Idempotent system should give you expected outcome whenever it is executed. Then we have observability. Every interaction and decision must be traceable via open telemetry, audit log. If you are building on Azure, you use Azure Monitor for monitoring and log analytic workspace, and you set metric for observability. If it is AWS, you use CloudTrail for log analytics and CloudWatch to collect, monitor, and then you analyze. So an orchestrated layer should be observable, observability should be integrated into the system. Then we have graceful degradation. So this is the ability of the system to fall back if an agent fails. So system must function with partial result or fallback if an agent fails. So failure of one agent should not cause the entire agent to fail. No, because you built 10 agentic system, and because agent number 10 fail, then the whole of the 9 remaining agents will fail. No, each agent should fail gracefully without affecting other agents or the orchestration layer. Policy-driven behavior is governed by, externalized policy, which are JSON rules. So we have what we call the policy as a code or governance as code, GAC or PAC. So policy are JSON-defined rules that is also integrated into the agentic system to govern, they are working to govern their activities, to monitor their performance, and to set guardrails and boundaries. That is, the agent cannot go beyond the defined policy to execute an activity, even though it can do it. So policy are guardrails or rules designed, to set boundary of activity, to set limitation for the agent. That is, they should have their boundary. They should have tasks that they cannot execute, and when they reach, when they get to those threshold or boundaries, human in the loop should be, called. That is why human in the loop is always, always very important. Do not give agent 100% autonomy when you are implementing sensitive enterprise task. So comparing the centralized and centralized pattern. So what are centralized and decentralized pattern? The architecture choice between strong global control and highly scalable peer-to-peer coordination. So centralized, orchestration, centralized multi-agent system is where, all the agents, are built together. They use one framework. Every agent uses one framework, and everyone just acts on their own. No, orchestration, no coordination and nothing. All the agents just exist and they talk together through one particular framework. Then we have decentralized. So decentralized, you have agents talking to each other. Agent can act independently. Agent can talk to each other. There's negotiation. There's assigning tasks and so on. And that is what you have here. So for centralized orchestration, let's define it this way. You have one orchestrated layer. All the agents are connected together through one framework. Then decentralized is where agent to agent communication is allowed through a particular rule system. So what are the features? Centralized orchestration and decentralized orchestration. Control. In centralized orchestration, strong consistency and global optimization is required, while in decentralized, autonomous peer-to-peer negotiation. So here you have agent-to-agent communication. In decentralized, an agent can also act independently, but for centralized, agents depend on the orchestrated or orchestrator to act and to perform tasks. They receive information from the central agent to perform their task, but for decentralized, agents can communicate with each other and can act independently without depending on the orchestrator agent. Scalability. Centralized orchestration is limited by the orchestrator bottleneck. So whenever there is a problem in the orchestrator, then there will be a problem in the other agent because they depend on the orchestrator to solve problems. Decentralized, they are highly scalable with no single point of failure. That is, you can design agent that will solve complex problem. You can design agent that will solve simple problem. And this agent still work together autonomously and can still, communicate through peer-to-peer negotiation while still working with the orchestrator layer. So that is the capability. Decentralized agents are used in, supply chain. They are used in blockchains as well. They are very good at that area, but I will not consider them good for enterprise, and we are going to see the reason very soon. Observability. Centralized agents, orchestrator agent are easy. They easy to reason about and debug. So you can easily debug or centralized agent. If there's a problem, you know who has the problem. There is a problem in the orchestrator, you know whether it is the orchestrator. If an agent has a problem, you know whether it is this particular problem or agent that has problem. But decentralized orchestration or decentralized coordination are very complex. They require sophisticated and distributed tracing. So that is why they are complex to design and the architecture is much more complex than centralized coordination. Resiliency, vulnerable to orchestrator failure. So centralized agents, they are not resilient enough, because when the orchestrator layer fails, all the agents will stop working. So there is no graceful degradation. In decentralized coordination, there's resiliency, because if an agent number 10 fails, agent 1 to 9 continue with their work without any problem. So resilient to individual agent outages. Best use case. Centralized orchestration is used for workflows with complex dependency. So they are used for designing workflows, and decentralized are used for high volume, complex tasks and complex systems that are loosely coupled and require loosely coupled interaction. So that is the difference. So centralized orchestration uses central orchestrator to communicate to all the agents, while decentralized design pattern, there is peer-to-peer communication and negotiation between the agent. The agent can bypass the orchestration layer to perform their task and communicate with other agents. So enterprise constraint. Production grade system must solve for legacy integration, data sovereignty, and strict access control. So multi-agent system is not trying to eliminate legacy system. No, it's building on top of them, making accessibility and getting data, solving problem, and working with integrate legacy system easy, and why reducing complex day-to-day activities of enterprise system. So they are there to assist and to build on top of legacy applications in order to ease their use and to make data accessible while giving an optimal solution. So enterprise constraint, what are these constraints? Number one, we have 500 millisecond timeout. So circuit breaker for strict SLA. So SLA, service level agreement. We can have this circuit breakers for strict SLA system, because legacy system, sometimes they don't even integrate well. So and you have surface level agreement and you have this timeout. Data sovereignty, enable GDPR compliant processes. So if you want to build a agentic system, multi-agent system on top of a legacy system, or integrate multi-agent system with legacy system, you must make sure you take note of GDPR, enable GDPR compliant processing, build governance, build policy following GDPR for the agents, and you should integrate this sovereignty into your design pattern. Multi-layer security. So before you integrate multi-agent system into a legacy system, you must make sure you design for multi-layer security, restrict across agent data access. So make sure you follow role-based access control and attribute-based access control. So assign, give limited access. If agent A is only to, go to solve IT problem, make sure you assign only IT problem. Do not assign them legal access or access to data that are not related to IT solution. You understand? So security, access control, minimization, and anonymization should be designed into the system. And then legacy adapters, modern JSON to SOAP XML payload. So, or make sure this multi-agent system also integrate with legacy adapters like modern JSON, SOAP, and XML payload. All right, strategies for global scalability at scale. How can you scale multi-agent system at scale for global enterprise? So architectural pattern to manage increasing agent population and high volume request bursts. So to scale multi-agent system, you should have agent pool pattern. So when you are designing the multi-agent system, make sure you design for agent pool pattern. That is, deploying multiple instances of agent type with round robin load, load balancing, and health check to prevent bottleneck. So make sure you use round robin, where the agent can use query to assess the agent that is healthy and assign task to the healthy agent using round robin load balancing. So in load balancing, we have what we call the round robins, and we have what we call the hash distribution. So round robin is always better for agent pool. Data sharding, routing requests to specific agent in instance based on entity. So agents should route data based on identity. Each agent should have their identity. Vendor agent should be assigned vendor ID. IT agent should be assigned IT ID. Legal agent should be assigned legal ID, and so on and so forth. So this enable data locality and efficiency for local caching. So whose data belong to who. Every agent will have their own database and their storage. Event-driven bus. So agents should communicate, loosely using event layers. So they should use asynchronous messaging, asynchronous communication to decouple agents, allowing the system to handle burst without cascading failure. So asynchronous is better because it allows the agent to solve problem in real time instead of in batch, because compounding problems can result in failure and degradation, which is not the agent will not be able to resist fault tolerance. Geo-distributed deployment. So running regional cluster to reduce latency, meet local compliance rule while enabling cross-region coordination for global tasks. So agents should be geo-distributed. You should design them region so that when there is a failure in one region, the agents can fail over to another region to continue operation. So you should not design and deploy agents in one region. They should be geo-distributed. You can use multiple regions or two or more regions, and within the region, use two or more zones. All right, quantifying the ROI, return on investment, of multi-agent system. How can you quantify your return on investment? How can you know you are gaining without losing from the design and from your spending on multi-agent system? So orchestration is labor saving, risk reduction, and cost scaling. Orchestration layer reduces labor for human and also for other agents. It's risk reduction. Okay, so we don't have much reduction because you know or when you use orchestration layer, I think the agent will be able to scale, and then you can easily quantify your costs without spending much for when you design for peer-to-peer or decentralized, where agent just communicate anyhow, because orchestration layer allow for governance. It allow the agent to follow predefined policy, and it allows the agent to operate within restrain costs in order not to incur costs for the organization. So there is risk reduction. It reduces risk of failing or of the old system failing, and it also scale costs. So you can design for cost optimization. You can design agents that will solve complex problem and assign them higher token, while agent design for simple problem can be assigned smaller token. So we have 10 times efficiency gains. Procurement time reduced from 80 hours to 8 hours. So when you build multi-agent system, you reduce human efforts, you reduce time to report and time to get value from investment, thereby improving the company's optimal solution. For example, building multi-agent system for procurement will reduce procurement operation from 80 hours to 8 hours, because when you use human alone or single agent, you just have tasks compiled in emails, whereas if you use multi-agent system, or every agent will be designed to solve particular problems, and they can operate in parallel and solve all these problems, 80 hours problems, in just 8 hours. And you have your value, you have your report, and you have your optimal solution, and then you can go on with other strategy and management without stress. Then 20% decision quality. So AI assisted legal reviews catch 20% more issue than human. This is proven and it works. So instead of one agent analyzing paper, or human being several 20 lawyers analyzing the same case, multi-agent system can analyze these skills in just 30 minutes, what would take the lawyers maybe 30 days to achieve. Then 2 times cost scaling. So 10 times volume increase require only 2 times infrastructure cost. So for example, in procurement, you can hire 10 people to do the same task, whereas you can build 10 agents, and these 10 people that you hire will be collecting monthly salary every year, and you can build 10 agents and pay and use the money, the salary of one person to or maintain this agent, and you still have value delivered earlier than the 10 people that you employ, and you keep the salary of the 10 of the 9 remaining people, thereby reducing your cost if the infrastructure is properly designed. So you can see the benefit. It reduces cost a lot. It reduces your time, and it improves efficiency, time to report, generate value faster, allowing the managers, the CTOs, CFOs, and the CEO to move on to strategy and think of expanding the business and handle tasks that agents cannot automate. Progressive adoption. So how can enterprise system adopt multi-agents? How can they adopt multiple agents or multi-agent system design? So we have 4 phases of implementation pattern here. So to reduce risk while building capabilities as well. So phase 1, single. So companies should not just start building multi-agent system. No, you'll be spending you'll be wasting system, you'll be wasting cost, because there should be a alignment, there should be information on how to use the agent. You don't just go ahead, and because you have a pattern, you don't just go ahead and implement all the pattern at the same time. No, start from single, scale to 2, scale to 3, scale to 4, scale to 5, until you can scale to 50 and determine that yes, the system is operative. So this is where many agents fail. This is where many companies fail, because they invest in multi-agent system from beginning and they did not see the value, because this agent cannot scale. They were wrongly designed, wrongly coordinated, and were designed to solve simple workflow that normal application can solve, or that normal Python function can solve. So you don't build agent for simple workflow that does not require complex thinking, complex evaluation. You will be wasting resources. So start from single agent. Start with one high capability agent to validate core functionality and establish performance baseline. So start from single agent and scale to multiple agents. Phase 2, simple. Introduce specialized agent for clear subtasks and implement basic central coordination. So in phase 2, you should now build a simple agent that can solve complex problem with coordination layer, not just build agent build one agent with the other agent. No, they will not be able to communicate, okay, through whether events or whether API or wherever. So when you introduce another agent, you should build a coordination layer, which is orchestration layer, that will allow the agent to communicate and solve problem independently. Phase 3, advance. Scale the agent population. So in step 3, you can now move to 3 agent, 4 agent, 5 agent. Because why? You have in phase 2, you have designed the orchestration layer, you have designed the coordination layer, and you have ensured that the second agent that you build can work and coordinate as well with the first agent without problem. Then scale the agent population, integrate legacy system, and implement good full governance and auditability. So at phase 3, scale the agents. You can build 3 or up to 5 agents here. You can improve your coordination and orchestration layer, implement governance and auditability, because now you have more agents working together. Then phase 4, this is where you optimize. This is where you improve the capacity, the performance, the reliability, scalability, and availability of the agent. Refine coordination logic based on operational data and optimize for cost using smaller specialized LLM. So this is where you build what we know as SLM, small language model, and then you optimize the agent, you increase their governance, their performance, their reliability, observability. Make sure you use all the metric that you are getting. Make sure you optimize for cost as well, and make sure you also design for scalability. Have agent that will solve complex problem, assign them tokens, higher tokens. Agent that will solve a smaller problem, assign them lesser tokens, and thereby you are minimizing a cost. So, all right, guys. So that's what we have in chapter 1, orchestration from single agent to multi-agent, scalability, optimization, when you should, the phases of implementing multi-agent system, starting from single agent to two agent with coordination and to multi-agent system. Then you scale and optimize while still maintaining your cost control. So this is what the architecture look like for coordinated or multi-agent system, from single agent to governed enterprise agent system. So here, in this book, we have used examples involving procurement, legal, IT operations, and supply chain only. So we cover these 4 examples in depth, and then these are the business domains that are discussed in the book. So strictly, we follow this business. We use them as example. Then you can extend from them to other businesses. And then layer 2, entry point triggers. So this is where you implement a request, user request, business event, document, system alerts. This is where they are integrated into the agents. Then layer 3 is where you have the multi-agent coordination core. So you have orchestrator agent coordinating all the agents, and you have all the agents communicating through the orchestrator and still communicating to peer-to-peer, communicating with each other. So look at the architecture for the orchestrated multi-agent system. We have the planner agent, we have the compliance agent, we have the analysis agent, we have the validation agent, we have the escalation agent. So the communication is bi-directional from orchestrator layer to each agent, bi-directional. Agent can communicate back and forth with each other and also with the orchestrator layer. And then phase 4, we have the enterprise control. This is where you give access based on what the agent is designed to do. So you give the planner agent the access it requires, give the compliance agent the access it requires, analysis agents, same thing to all the agent, and even the orchestrator agent access. So this is where you build and integrate governance, security, observability, human in the loop, and audit trail into the agentic system, into the system architecture. And then we have layer 5, which is the final layer, which is called the integration layer. So when you have everything ready, then you integrate the agentic system into the legacy enterprise application. So enterprise system and data. So you connect the agent to databases. You already give restricted access to using role-based access control or attribute-based access control, and then you integrate into the ERP or SAP system and applications. You integrate into the CRM and ITSM applications. You integrate into the databases. You integrate into knowledge base of your vector database or your RAG system to augment the information and improve the accuracy of the output of the agent. And then you also integrate into external APIs. Okay, so if you follow this 5 design pattern, then you are building an agentic system or multi-agent system that is reliable, coordinated, traceable, and you know, giving you optimal business value. So this is the architecture in practice. So if you follow this architecture in enterprise multi-agent system design, then you are building for reliability, scalability, performance, and availability. Okay, so key shifts: single agent, so shift from single agent to coordinated agent. Okay, so answering, executing workflow. So instead of building workflow, build a distributed system, and that can communicate with each other while still acting through the orchestration layer. Then demos, make sure, don't just jump into production. Make sure you build a demo before you build a production architecture. So this is the end of what we have in chapter 1, guys. So I'm going to post the link to my website for consulting, for book purchase, for journals, and everything. So please visit the website, drop your email to receive newsletter from me whenever we post. There's not going to be any spam, just information, right information at the right time. Also click on the link on Amazon to purchase the book, on Seller if you're in Nigeria to purchase the book, available in Naira to all users. Thank you everyone for listening, and do well to subscribe and like our channel.